Well, okay, guys, this is a video to show you how are the graphs of some functions that you have never ever saw before. So we're going to start with the absolute value function. Remember that the absolute value of a number is the distance the number is from 0. According to that, we are going to work with this function. The symbol for absolute value is the letter X in between a couple of bars, as you can see here. And this is the definition of this function is given by two different rules. Because if the value of X is positive, like you can see here, if the value of X is positive, the absolute value of X is also X. For example, the absolute value of 2 is 2 because 2 is positive. But on the other hand, if the value of X is negative, the distance a number has is always positive. Therefore, for example, the absolute value of -5 will be 5 because -5 is 2 units away from 0. So when the value of X is negative, instead of replacing in this first expression, you are going to replace in the second expression. It's quite simple, the concept. I know that this definition might look confusing, but let me show you what happens. When X is positive, you have all the points of the absolute value function on this line, which is y equal x. It's this line here, you see? And since the absolute value can never be negative of a number, because no matter if the number is positive or negative, its absolute value is going to be a positive number, this part here below the x-axis does not belong to the graph of the function absolute value. You see, because all these results, the results corresponding to y equal x for negative numbers is negative. So it's like if you cut your line y equal x here in the origin of coordinates and you make a reflection of the other part with respect to the x-axis. And then you form this part here. Or either you can consider it as having this line, which is y equal minus x, is the line you have here, and make exactly the same thing, but for the positive values of x. So since this part cannot be negative, just because the graph of the absolute value function can never be below the x-axis, if it's of x, of course, it's like making a reflection of this part of the line with respect to the x-axis. Okay, the graph then of the absolute value function will always be a V, a short V, okay? Always be a short V. So every time you see a graph with a short V represented, you have to know that that is an absolute value function, okay? Let's take a look to some of the transformations happening to this function absolute value. Let's start for this one. And let me show you a point on the graph of this function. As you can see, here you have 2 added to x inside the absolute value bars. And this, as regularly, implies a translation horizontal by 2 units to the left, because remember that every time you have a transformation, horizontal transformation, whatever it is, you are going to take the reciprocal of the number which is multiplied or subtracted or added to x inside, affecting only x and not the full expression of the function. So how can you realize if you are not given this, the expression of the function? Okay, by comparing the values of y. So, by comparing what happens with the values of, for the same value of y, what happens with the values of x. Okay, so the values of x coordinates of these 2 points, the red, which is a transformed one, and the green, which is a basic one, these 2 points are 2 units apart in the horizontal sense. So it means that this point here, point D, has been transformed into this point C by moving the full graph of the function 2 units to the left. Let's go for the following one. This is the blue one, okay? And in the blue one, we have, in this case, some values of this expression, of this function, which are below the x-axis, in fact. And you might ask me, but Miss Carla, you said that the absolute value function will never be 0. Yeah, of course. The absolute value is never 0. But in this case, the absolute value has 1 subtracting from it. Because as you can notice here, the difference with the previous one is that the number added was inside the absolute value for bars. And in this case, you have it outside. So every single value in the green curve has been moved down 1 unit. And in this case, this graph resembles the graph of a parabola with its differences, right? Because here you also have 2 branches, and now you have 2 x-intersections that you before didn't have. Before you only have had 1 x-intersection, and now you have 2, okay? How do you realize this? Okay, you trace a vertical line in any part of the 2 graphs, and you compare the y coordinates. As you can see, the x coordinates are the same in this case, and the transformation has affected only the y coordinates by subtracting 1 to the existing one. So this is a vertical translation by 1 unit. Here we have another transformation, which is, in this case, a stretch. Okay? In this specific function, you can say that this is a horizontal transformation, sorry, as a horizontal stretch, or either a vertical stretch, because it fulfills both conditions at the same time. So no matter if you identify this transformation as a horizontal or vertical stretch, as long as you give the right stretch factor, your result is going to be considered as right, and you're going to gain full marks in the exercise appearing like this, something like this. Okay, so in this case, I will consider this a horizontal stretch because the number is multiplying x, the constant 2 in this case, is multiplying x inside of the absolute value bars. Okay, so if I trace a horizontal line here, and well, sorry, this is here. So if you trace a horizontal line, what you are going to see that the green point here is at 2 units, is 2 units away from the y-axis. But this orange point is half of the distance from the y-axis. The scale factor, or the stretch factor in this case, for this function, for this transformation, is going to be 1/2. Remember that what you do is to take the distance from the y-axis of the transformer one, and you make the ratio by dividing it by the distance of the original point to the y-axis. In this case of this stretch, it's easy to mix up these 2 transformations. But don't worry, because it is going to be all right as long as you give the right stretch factor to justify your decision. So in this case, we have another stretch, but pay attention here. You have 1/3 multiplied outside the absolute value bars. In this case also, you can confuse this with, which is a vertical stretch, with a horizontal stretch. But what we are going to do now is to take, sorry, I am going to move this one here and this one here. And if I trace a vertical line, the distance these 2 points are from the x-axis in this case, remember that in the previous one, we have taken the distance to the y-axis. In here we are going to take the distance to the x-axis, okay? Is 1/3 of the original distance, because here you have 3 units away from the y-axis, sorry, from the x-axis, and here you have only 1 unit away the graph from the x-axis. So your stretch factor is going to be 1/3. The branches are more open, are wider than before. So with this, we are done with the absolute value function. One more thing before we pass to the following one. If I take, for example, the absolute value of, minus the absolute value of x, look what happens. This is a reflection with with the mirror line, the x-axis. So it's the green function, but turn it upside down. So in this case, you are not going to have graph in the upper part. What this does is to change the range. Remember that the domain, you measure it in the horizontal axis, in the x-axis, and the range, you measure it in the y-axis. Let's pass then to the following function. Sorry. This is an exponential function. In an exponential function, let me move this here. In an exponential function, examples of exponential functions are functions where the variable, instead of being in the base of a power, like for example in any polynomic function like the quadratic function, you have x raised to a power and that power is fixed, is a fixed number. In this case, you're going to have the other way about. You're going to have a number which is going to be the same for all values of x and y raised to the variable. What is going to change is the exponent. So here you have the expression of the basic exponential function. Is a fixed number raised to the variable x. This number here, the base of this power, can never be lower than 0. Okay, here it says it has to be greater than 0. Why this number cannot be negative? Because remember the rules of signs of the exponentials, of the exponents, of the powers, okay? So when you have a base and the base is positive and you have any exponent, the result is going to be always positive. And if your base is negative, signs changed because of the kind of exponent you have. If the exponent is even, you will always have positive results. But if the exponent is negative, you are going to have a negative result when the base is negative. And another problem we have here is that for negative numbers, not all roots which imply, remember, an exponent which is a fraction, have solution in the real number set. For example, if I have the square root of -4, remember that the square root is an exponent 1/2. So if I have an exponent 1/2 and I have a base which is negative, that has not a solution in the real number set. So negative numbers as bases have many issues in this case, and it doesn't allow this expression to become a function. You cannot join the points also. That's why the value of a must be always, the value of the base must be always positive. Another issue we have is the base being 0. The base can also not be 0, and the base can also not be 1, because in the case of 0, all powers with the base 0 are going to be equal to 0, and any power of 1 will still be 1, so you don't have function there, because for every single value of x, you have only one value of y. But let's take a look to the expression of this function 2 raised to the x power. If I have 2 raised to the x power and the exponent is positive and it starts growing and growing, you are going to have values of y which are going to increase without any limit. Look, if you have 2 raised to the first power, you're going to be here, is 2. This is a little bit here. If you have a 2 raised to the third power, you will have, an 8, which is far away above. Okay, and in the meanwhile, in the middle, in between 2 and 3, you're going to have infinite points because 2 is going to be raised to numbers which are going to be decimals. What happens if x is 0? Any number raised to the 0 power will be 1. So for 0, you are going to be in the y intersection, which is going to be always 1 if the transformations you applied to the function leaves you an exponent in x. And what happens when the values of x are negative? Remember that when you have a negative exponent, the base turns upside down. So this 2 is going to turn into 1/2. So 1/2 raised to the first power is -1. 1/2 raised to the second power is 1/4. 1/2 raised to the third power is 1/8, and so on. And those values are going to grow closer and closer to 0. But they will never be 0. Remember that the only way of having a 0 in an exponential is when the base is 0. So in this case, you will have an asymptote, a horizontal asymptote in the y equals 0. Okay? Let's start going for a translation, a transformation, whatever. So in the first case, I have 2x number 2, raised to the power of x minus 2. And as we could expect it, the green graph has been moved horizontally 2 units. Here, let me move this point so as you can see what happens with the coordinates. The value of y remains the same, and the value of x has been increased in 2 units, because since you have here -2, that is a horizontal movement as long as this -2 affects the x. Okay, so the horizontal asymptote is not going to be modified, but the y-intersection will be. Okay, the y-intersection will change. Here we have it in 1/4. Okay, let's move to the following one. What happens if I add 1 to 2 raised to the x power? So then the graph of the function will be moved up by 1 unit. Let me show you a point here. So the y-intersection has been moved 1 point up. And for every single values of x, you will have a difference of 1 in the y coordinate. For the same value of x, you will have the values of y increased by 1 unit, departing from the green one to the here to the violet one. Again, the horizontal asymptote doesn't change. Okay, let's move to the stretches, okay? So here I have a vertical stretch because the number is multiplying the full exponential. 2 raised to the x power multiplied by 5. So let me show you a point and let's try to make our conclusions, to draw some conclusions. These are the coordinates of point B, which is this one red. And as we can see here, if we pay attention what happens to the y coordinates of these 2 points, we're going to see that the point green has been multiplied by 5, the y coordinate, of course. Let's see what happens, for example, if we moved to -1, we are going to be in 0.5, and if we move this one, the red one, to -1 here, we will find that the value of y has been multiplied by 5 because 0.5 multiplied by 5 gives you 0.25. So as you can see, if you cut both functions with vertical lines, the difference in the y-axis, in the y-coordinates of those points, is going to be by multiplying the original one by 5. 5 units multiplied by. Okay, let's see finally what happens with the horizontal stretch. Here we have a horizontal stretch, and if the first thing that calls our attention is that both functions have the same y-intersection. You see, both functions have the same y-intersection, they share it. And if we move to a point, for example, this point 1, 4, and we moved the green one up to the same height, for the same value of y, we have our stretch factor, which is going to be 1/2. Remember that you have x multiplied by 2, the stretch factor is going to be the reciprocal of 2. So you're going to have the stretch factor will be 1/2. If you have it multiplied by 5, will be 1/5. If you have it multiplied by 1/10, you are going to have a factor of 10. Okay, so the yellow or orange point is halfway from the y-axis than the green one. Halfway. Thus, the stretch factor is 1/2. Okay. Well, and now I have left for the last moment this one, which is a polynomic function. Let me show you in detail. A polynomic function is any function which expression has x raised to 1 power or several powers, which are all natural numbers, okay, including 0. So for example, you know already some of the most known polynomial functions. The linear function is a polynomic function because you have x raised to the first power. And then you have another term, you might have another term with x raised to the 0 power, which is a constant term. For example, if you have 3x minus 2, x is raised to the first power is multiplied by 3, and the minus 2 is multiplied by x raised to the 0 power. But since anything raised to the 0 power gives you 1, you cannot see the x raised to the 0 power. And you also know the quadratic functions. You see, the quadratic functions might have at the most 3 terms, and in each of the terms, those terms are never like terms. So you are not going to be able to simplify them. And this little x squared could be added to another or 2 more expressions in x. If you add a linear to x squared, you're going to have a quadratic. Well, the new ones are these ones. The cubic function has this shape, the basic one, 1 x intersection, 1 y intersection. But the cubic function can take a uh, very wide amount of different shapes. For example, let me show you some. They are crazy, really crazy shapes. In this case, is also cubic function, but as you can see here, it has 1, 2, 3 intersections with the x-axis, and only one with the y-axis, of course. Or either I can have this one, and this one is also a cubic function. Okay, let me move this a little bit up so as you can appreciate the difference. Here we have a cubic plus 3 other terms, and these 3 other terms are a quadratic term, a linear term, and a constant term. And the amount of solutions, of roots, of zeros of this function are just 2. So a cubic function can have at the most 3 roots, 3 solutions, or 3 zeros. In general, polynomic functions can have at the most as many solutions, zeros, or x-intersections as the maximum power of x. In this case, you can have either 1 intersection, 2 intersections, or 3 intersections. Is it necessary for you to identify the cubic function just with a glance? No, only the basic one. You should know what is the shape it has. That is very useful. You're going to see it. But the real shape of any other of those, you don't need to know them. The kind of exercises you're going to receive are exercises where you have drawings of functions, and with this idea of the number of solutions or the number of zeros the graph of the function, polynomic function, might have, you can have an idea if it's polynomic or not. You need to identify a quadratic from a cubic. And I believe that with these hints, you're going to be able to do that. Remember that the quadratic might have at the most 2 solutions to x-intersections. But there are more. We also have the quartic function, which is this one. It's like a parabola, but it's kind of heavy parabola, you see? And as long as you cannot identify here that there is only one x-intersection, only one solution, only one root, because it's like a flat tire. You see, it's like a flat tire. When the tires of your father's car it needs more air, it starts to being flatter. Okay, flatter and flatter. In this case, there is only one point of intersection with the x-axis, only one. Take a look here, please, to the expression. When r of x is 0, 0 equals x to the 4th power. And there is only one value of x that makes the expression 0, and it is 0. So the rest of the values that you can see here kind of sitting down on the x-axis, in reality, they are very, very, very tiny separation with the x-axis. They are not touching there. There is only one touch. And we have also this shape for the quartic. It's weird. Or this shape for the quartic. And I now have another one. This shape for the quartic. Okay? All those are quartic functions, and it's the same idea as the previous ones. You might know, you will need to know that the shape of a quartic might resemble to a quadratic function, but it is not. And in general, the quartic functions you're going to find are functions which have more than 3 zeros. Okay, in this case, we have 4 zeros. In the previous case, we've got 1, 2 zeros. And in the previous one, sorry, we've got only 2 zeros too, okay? And you might have some points of inflection, which are the points or turning points where the curvature of the function changes from up to down, but without provoking a next intersection. Another thing that is quite interesting to know about the polynomial functions is that they in general have, you can identify them because they have minimums and maximums. Remember that the quadratic function can have either one minimum or one maximum depending on if the branches are upwards or facing down, okay? But from the cubic one and on, you know that those functions might have more than one minimum and more than one maximum, or either have a minimum and a maximum in the same graph, okay? Here, let me remove the other ones so as you can see it properly. Here you have, look, 2 minimums and 1 maximum. In this case, we call the minimums and the maximum local minimums and local maximums. The maximum among all the maximums is the absolute maximum, and the minimum of all minimums is going to be the absolute minimum. But that's not really something that you need to know right now, okay? But just take under your scope that these functions always have minimums and maximums, okay? And then, well, you have quintic functions, which are polynomic, fifth degree polynomics. So are expressions which contains x raised to the fifth power. You can have an octic one. This is an octic function, which is flatter, more flat than the quartic function. Okay, I believe that with this we are done with this kind of functions. The only one function remaining are the logarithmic function that we are going to work with it when we come back from the winter break, and trigonometric functions that we are going to attack in any moment during the following months. Okay, well, I will leave you now, telling you that I love you, and I am hoping that this video was helpful for you, and I believe that this is going to be extremely useful for the students who got connectivity issues and couldn't be attending the class where we work this. Okay, see you shortly. Bye.